Okay, so this section is all about the mass spring oscillator. So if we're talking about mass springs, that means we're going to be using Hooke's law to do spring conservation and stretching and compressing. Okay. So Hooke's law basically says it's used for springs all over the world, like gyms use it all the time. Anytime we have a rope or a spring, Hooke's law is actually, always useful when it comes to this. Now, according to Hooke's law, we have a force that's directly proportional to the displacement of y. So y meaning the process pushing in this right direction. So here's our force. So the force of the spring is equal to some constant k times y. So this spring constant is changing from spring to spring, but the reason why it's a constant, because after you find that constant, how you compress it or stretch it out will be the same process, right? It's hence why it's a constant. Now, the equilibrium point, basically, we'll talk about that in a little bit, is, well, at this point in time, it's essentially zero. So when we compress here, it's going to be negative, and when we stretch, it's going to be positive in that direction. And the y value goes in this way, either this way or this way, depending on what we want to do with the spring. Okay, so the question now becomes, how do we do when we come to compression? So when we compress something, like if it's on a wheel, we have an opposite force pushing against it called the friction. Okay, so this friction force is a derivative of y, and it looks like this. So it's minus by prime. So after putting everything together, we do have another force. If you go into physics, you understand that process. Usually called a damping constant. Well, the B is called the damping constant. But the other type of situation is anything in process besides friction. It could be in movements, gravity. Obviously gravity is a big one, pushing down all the time. Electrical forces, magnitudes, and all that fun stuff, right? So there's an alternative to that. So putting all this together, we have an external force being moved in both directions we want it to. And it's a combination of these put together, which gives us this part and that part. And this external force that we don't really have apply goes here, which is the second derivative of y. Okay. So this is our technical term when it comes to mass spring oscillation. So what we want to do in this section is, given a scenario, can we verify if the solution actually matches this, or can we actually find the exertion or each individual case that exerts this force based off the spring? So let's see. So we want to verify that if B is equal to 0, the force exerted on it is 0, and y of t is equal to cosine of omega t, is a solution to our function. So we have their situation here, so we're just going to plug in each individual case. So B is going to be 0, so that means this just goes away, and this side is just equal to 0. So this ends up being our equation. Okay. So if I just bring this over, for instance, we need to show that these actually equal each other. So using our y value, so have y is equal to cosine omega t, or just wt. So we need to take the second derivative, so we'll just go down in order. So first derivative cosine is negative, and it's a chain rule. Yeah, it's a chain rule. So derivative of the inside is just w with a negative in the front. Now it's sine. Take the derivative one more time. So basically the same thing. And now we just want to verify if we plug in our y and a y double prime into here, do we actually get the same thing back, right? Because it should be actually 0 or just equal each other. So plugging this in, so it's going to be negative n times all of this. So negative, negative, make it positive. And this times k. So if I divide everything by cosine WT, these end up just canceling each other out, and we're just left with mw squared is equal to k. So if I divide by, or if I solve for w, so w is equal to plus or minus the square root of k over m. Now, since we have to make this be positive, so in other words, this will only work out if w is equal to the square root of positive k over m. So it works out. So, right, very theoretical, since we're dealing with the variables itself. So why don't we do one a little bit more concrete? So we want to verify the function y of t equal to e to the negative 3t is a solution to our external forces where all this matches. So this time we have a little bit more applied stuff, numerical values themselves. Okay. All right, so we just plug in each one. So this is going to be 0 is equal to, m in this case is 1. So we just get y double prime. B in this case is 6. And then finally k is 9. Alright, so we just want to verify that this is true. So we'll go back over here. And our y initially was e to the negative 3t. So we need two derivatives. So again, this is just a chain rule. And one more time. Another chain rule. That gives you positive 9. Okay, so now we just plug in all three into here and see, do we get 0 when we add subtract. So it's going to be this one first. And just don't forget you're supposed to multiply respected by each one. So 6 times this part will give you negative 18. And then plus 9 times this. And it looks like we actually do cancel away. So it does actually work. So yes is the solution. Okay. So let's do one that's not very fun to do. So find the value A such that the mass spring oscillator with m is equal to 1, b is 1, k is 25, and the force is sine of AT. So very similar to what we just did above, right, where we solve for the W value that makes this work. Okay. But why is this not so fun if it kind of looks the same situation we did over there? The reason for that is because now we actually have a force. It's not 0 in this case. So like all the other times, that was 0, and so was this. So this equation now becomes sine of AT is equal to, and we'll just follow the template here. So m in this case is 1, so we get y prime, plus b is also 1, so y prime there. And then finally k is 25, like that. Now, notice we don't have any situation happening here, right? Now, this goes back to understanding how to solve for the system of equations. Knowing that this derivative somehow has to be in terms of, sine itself, and a general y value, if we just put sines, it will eventually somehow cancel. It may be a combination of just sine and cosine. So we're just going to guess of something like this happening. it's some form of that. And now if we just take the derivative twice, negative, sorry. This is positive. And then take the second derivative again. And this becomes negative. So plugging all of these things into here, so it's double prime, oops, plus all of this. Finally, plus 25 times that. Oh boy. Right. Now, this is kind of the same process when you do partial fractions, where you want to set everything equal to what it's supposed to. So since we're dealing with just sign, pretty much all this is equal to 0. And the addition of these individually equal to 1, so that's the number in front of sign, and the number in front of the cosine will all just equal to 0. So this plus that will equal 0, while the other ones will equal 1. So knowing that aspect, it kind of breaks down this a little bit. So now this becomes 1 is equal to, so minus, yeah, minus a squared b, and here, and then finally plus 25b. This would be here as well. And now 0 will equal the respective parts of the cosine. Now, at this point, this is why it says not as fun example. So you have to use a lot of algebra and a lot of manipulation to solve for this system of equations, or just basically solving for b and a, or capital A and capital B respectively. So after a lot of work, we eventually get capital A is equal to minus a over a squared plus a squared minus 25 squared, and b is equal to negative a squared plus 25 all over the same thing. And believe it or not, actually plugging everything in for a and b into here, or let's say just one of them, and eventually solving for a, we get a is equal to 5. So this is where computer-generated software comes into play much handy, when, trying to figure out interface and forces applied to certain objects based off what the function represents. And it's much more difficult when you have a force that's not zero, since, it gets a lot more tricky, especially if the sine waves oscillates back and forth, right? So the same process you would have to use when you have cosine. So any oscillating function isn't really fun. A lot of the times, a lot of this process gets generated using computers because, doing it by hand is pretty much very, very difficult to do.